Welcome to Statistics Former Student Network, SFSN talk. Today we are really excited to have our alumni, our former student, Liang, who is going to give a talk. Let me say a few words about Hua. First, my name is Brani Vidakovic, and I am the department head of statistics at Texas A&M. Liang is a professor of statistics and biostatistics in the Department of Statistics at George Washington University. Dr. Liang received his PhD in mathematical statistics from the Institute of System Science, Chinese Academy of Science in 1992, and his PhD in statistics from Texas A&M University under the direction of Professor Raymond J. Carroll in 2001. He was an assistant professor between 2002 and 2005 at St. Jude's Children's Hospital, associate professor between 2005 and 2009, and professor between 2009 and 2013 at University of Rochester Medical Center before joining GWU. Dr. Liang worked on semiparametric regression, mixed effects model for longitudinal data, measurement error models, high-dimensional data analysis, functional data analysis, and HIV dynamic models. He has been awarded 2 R01, 1 T32, and 5 NSF grants. He is a fellow of ASA, IMS, Royal Statistical Society, and member of the International Statistical Institute. Dr. Liang has served as an associate editor for Biostatistics, Electronic Journal of Statistics, and JASA. He has published over 180 articles. Additionally, he was awarded the H.O. Hartley Award in 2012. Dr. Liang, we are pleased to have you, and please take over for the talk.
Okay, thank you so much, Barry. Thank you for your introduction. It's my great pleasure. Also we cannot see each other in personally, so I feel still excited. And it's always my dream place. Even after 20 years, sometimes I still think I miss the college station. So when I was asked to give a talk, of course I'm really excited and immediately think about what I can talk about. But consider the audience for wider audience, so I pick up just make it easy. Talk about the semi-parametric model, but we don't know any technical detail. Just to show you some idea and example. Actually, some example actually from my publication to show you how good or useful of semi-parametric model. So in my talk, first again I will give some brief introduction. For instance, what is semi-parametric model? What is the method we generally used? And then specifically, I will talk about a little bit more partial linear model, partial linear additive model, generalized partial linear additive model, and the last case actually with high dimensional. So so for those partial, it's just because I working on those area even before I joined college station. So we all know, if we wanted to type of models, we have a standard linear model, generalized linear model, non-linear model, or non-parametric models. And for the non-parametric models, then we can also a little bit more separate to like an additive model or generalized additive model. And if we think about it like the regression method, then of course we have like a general linear regression, non-linear regression, robust regression, non-parametric regression, and parametric or non-parametric survival regression, and the semi-parametric regressions. So what is the semi-parametric model? Actually, I checked. So far, it seems no very rigorous definition. But for those descriptive definition, I think it's pretty easy to understand, except roughly speaking, a semi-parametric model actually is just a combination of parametrical and non-parametrical. Okay, what the model is exactly a parametric model, or what is exactly non-parametrical or semi-parametrical? Sometimes may not that clear. And of course, for semi-parametrical model, we immediately got a lot of examples. For instance, here, very famous Cox proportion Hertz model, right? So in this model, we have an unknown function lambda 0 u, and but we generally are more interested in the primary parameter beta. So this is a semi-parametric model because easy we have a parametrical and non-parametrical. And the second one, I highlighted here, of course, this is a linear model, and so most time, of course, we think, of course, this is a parametric model. However, if we don't make any, distribution assumption for the error term epsilon, so and if we are, studying like a, estimation efficiency of for beta, actually this we can also think that this is a semi-parametric model because beta is a parametrical, and but we don't know what's the distribution of epsilon. And a very important paper actually by I think by Stone in 1975. Actually, he studied additive estimation for beta for this model, but at that time maybe he didn't call it a semi-parametric model, but later actually people classify this as a semi-parametrical issues. And the third one, we single index model. So this one is a generalization of linear model. We have a link function S. S is an unknown function. So this is a very typical semi-parametric model. And the fourth one, a partial linear model with a partial linear X transpose beta plus another unknown function GZ. So this we call partial linear model. So this sometimes some people think this is just a semi-parametric model, but of course the semi-parametric model with a much wider coverage. So here I searched from two major databases. Actually, I did maybe last year or 2 years ago. I just used the semi-parametrical as keywords. Searching from ISI and MSN to see how many publications. So here, the green line actually is based on ISA website, and the red line based on American Mathematical Review. And I also, separate those the borderline. I just counted, how many published in that the 5 top statistical journal: Annals, JASA, Biometric, Econometric, and JSSB. So roughly, actually, the popularity of a semi-parametric model actually almost started from 1984 or 85, and then increased until to 2014 or 16. Then the trend slightly or you can say slow down. But for the that the 5 top journals actually specifically show us they are similarly every year they publish maybe about 10 or 8 papers, but mostly actually they publish JASA. Totally, JASA published 151 articles related to semi-parametric models. Of course, this may be not very accurate because some authors didn't use those semi-module in their in their paper titles. They may be overlooked. So again, from 19 to 2010 or even a little bit later, so semi-parametric model seems very popular topic, and also here, I found at least 10 books that talk about the semi-parametric model. The first one, by Peter Bickel and John Warner, actually is my favorite. They talk about the efficiency and adaptive estimation. And then Wolfgang Hedler, my host when I work in Hongbao. And then Hastings Tibichinani and John Corwitz, Kiro, Mike Costco, and Davey, and Ray, and Giatis, and Sam Woods, and Yachios. So most work either theoretical or some actually application. So again, maybe more actually. We also published a paper, a book called Partial Linear Models. So for semi-parametric model, because it is a combination, that means if we want to do estimation or inference, very intuitively, we'll just combine parametric method and the non-parametric method. So for parametric method, maybe we use a least square or likelihood based or moment based or robust. And for non-parametric regression, we kernel regression, regression spline, smoothing spline, penalized spline, wave rate, and also a lot of other, so we can combine those each one. For instance, least score with a regression spline or likelihood based with a penalized spline. So then we can do some estimation for semi-parametric model. And again, for instance, for linear model, we know the least square estimator, it's very simple, but with a very nice statistical property. For instance, asymptotical normality, and in certain situations, for instance, based on Gaussian-Markov theorem, we know it is the best one, right? On the other hand, for the non-parametric regression, it is very flexible. No any strong assumptions on the function mx. However, we know, for non-parametric regression, we generally cannot get a root n consistent estimate. So we generally have those convergence rates depend on the dimension of the x. And for semi-parametric, because it is a combination compromise. So intuitively, for instance, here as example, I wanted to show you. For those non-parametric, we have a curse of dimension problem. So what it means, curse of dimension problem? Here, I just show you one table I copied from, I think, from David Scott's book. With that, increase the dimension of x. So if we want to get the equal precision as the as the linear model or parametric model. So for instance, if we have 10 observations for one dimensional, and then we have 20 observations for two dimensional. So we just go 10, 20 until to 100. However, if we want to get the same precision as for parametric model, for the non-parametric, how many samples do we need? For instance, if x increases to the dimension of x increases to the 5, then we need, Silverman scored, they use a slightly different criteria, but got those different numbers. So for instance, for those one, so it means if we want to get the same precision as parametric, we only need 50 observations. However, if we use a non-parametric with 5 dimensions, then we need 6,000 observations. So this actually dramatically challenged us, for those because of dimensionality. So that's why we try to combine. One side we want to make the model as simple as possible. For instance, like a linear model. On the other hand, we also try to enjoy the feasibility of non-parametric model. So partial linear model actually is a very typical example. Those combination here, if we are based on our previous experience or example, we know x contribute y still linearly. However, if z actually is non-linear, or even we don't know what the closed form, then we think about those partial linear model. And for those partial linear model, of course, we are definitely interested in to estimate the beta and also g. And intuitively, because of this, the right side already contain the non-parametric terms. So intuitively, it seems the essence of beta in this model may not able to get a root n consistent anymore, because intuitively we cannot get a root n consistent estimate for gz. So this is very beginning intuitively indication. However, several people make nice contribution. Here I just show you, how do we estimate this one, like we call pre-smooth, or actually next page slides. So for instance, Grace Waba, Unger, and Nancy Heckman, Paul Spigman, and Hong Chen, they are developing the different method to estimate beta and the GZ. One called partial spline, one called pre-smoothing or partial regression smoothing spline, or two-stage, or whatever. The estimate of beta actually can. Here is an example. For pre-smooth, we just take the conditional expectation of y given z, and then use the original model to minus. Then this model actually is like a linear model if we can estimate those two conditional expectations. And of course, those two is available based on data. So after we do such a univariate regression, then we got the linear regression model, and the estimate of beta actually, based on those model, still, can be proved asymptotically normal and with root n consistent. So for such a nice asymptotic result of a little bit of surprise at that time, but of course right now everything seems very transparent. It seems also pretty easy. But at the beginning, I think may not. Okay, so I briefly mentioned the semi-parametric model. I give you an example. So now let me show you some real data examples. So the first one actually it's talk about the relationship between the salary and marketing experience. This is real data from Germany when I work in Berlin. Wolfgang Heder asked me to do one data analysis. So our Y is owner salary, and we of course include other variables like demography and others. But Z actually we feel the lab market experience should treat as a non-parametric. So here is the fitting for that non-parametric terms. So you can see roughly speaking, this actually 0 actually it means 6 years old, because 6 years old people study go to school. So that means roughly speaking, most people got the highest salary about 46 years old, or maybe 50, something like that. But after that, the salary may not increase anymore. So this of course is very pretty natural, because after those age, most people may not ever that more energetical, and the best time or almost go. Okay, so this is one simple example. Use a partial linear model to study the relationship of the salary and the age or the marketing experience. The second one is it's a study of nutrition epidemiology from our statistical cynical paper. So in this example, we talk about the relationship between proton beta calorie level and person characteristics and the dietary factor. And so the response variable is a log data carries level, and the personal characteristics including age, gender, BMI, and the dietary factor including calories, fat, fiber, alcohol consumption, and cholesterol, and other smoking status. So for this data set, if we excuse me, if we use the linear model to fit the model and to make a more emphasize for those variables with p values small. So we feel BMI and the 5, gender, and the smoking seems significant, but the age and the cholesterol level seems not. However, when we make a future investigation, we found that the change of the age and cholesterol, actually it seems shows non-linear. So that means based on those future investigation, it seems we actually preferred to use those two terms to replace the previous non-linear terms, and also in the non-linear terms, we based on those values. The age actually show us the p-value actually seems on the borderline, but the cholesterol level actually is totally no significant. So, and this of course not surprise if we use straight line to replace those curves, then this will almost give us a horizontal line. So that's why show the p-value are not it's big, and so it's not significant. However, of course we know they are significant and give us pretty interesting pattern. It seems the cholesterol level if too low or too high seems not well. So this actually is a kind of partial additive linear model, because here we have two terms, both are non-linear, actually unknown functions. Okay, so the third example is generalized. It means now if we think about for instance, the binary response variable y. So in this case, we need a link function, so mu. Okay, so the inside is still kind of partial linear and additive, but we put the generalized because we have a link function. Of course, those link function is null, and only beta and those theta are unknown function. And this, of course, is also a generalization of partial linear additive model, because if mu is identity function, it will be PL AM. Okay, so for the generalized case, we're not talk about the more like algorithm or theorem. Here, just to show you one example in our annals paper, talk about a study about diabetes. By the way, the algorithm in our paper already programmed by Jonas Mueller in the package PLMDE. So here is the data. Y is the indicator of a positive test for diabetes, and then all other covariant like a number of fragments and diastolic blood pressure, diabetes pedigree function, and plasma concentration, and the BMI and age. So the data actually is not that complicated. But by the way, this is typical data from I think Arizona, some special African American female. So for this one, of course, we interested in which variables may significant impact the positive test for diabetes. So again, for those topic or questions immediately, of course, we can use logistic regression. And so if we use a logistic regression, we found the number of fragments, diastolic and progress and the BMI are statistically significant, but diabetes and age are not statistically significant. However, here is the curve or a pattern based on our study. For the age, actually, it also show us those mountain shape. For the BMI, it's slightly nonlinear curve. So again, think about for the wait a second, my table. Okay, here is the table. So if we use a logistic to fit the data, then on the other hand, if we use the generalized partial linear additive model to fit the data, we got for some variables they show us either significant or no significant, but the challenge or the interesting is for the age. If we use the logistic, it seems the p-value is 0.08. However, look at the curve of the age. So we feel actually this show us some interesting information. It means this for those group at the about 50 years old, they have a highest risk to got the diabetes. But if we use logistic, actually it seems to show us no significant. Okay, Adam asked me a question how to interpret the y-axis in the non-linear effect. Okay, I will mention this a little bit later. Okay, thank you. So for those one, of course, we have a dramatically different conclusion if we use logistic or generalized case. And well, this is a new real data. We don't know what to choose, but at least data analysis already show us different. So then we actually run a simulation. We run a simulation. So how do we do that? We actually simulate the data or generate the data based on our estimation result, but use the model with non-linear. So that means our model is not traditional logistic model. However, we use the logistic model to fit, and we repeat it 5,000 times. So in this case, actually we got about 67% number of recurrence significant, and for all other diastolic and diabetes pilgrims and concentration BMI in the ages, they are got 4%, 90%, 100%. So for those one actually can somehow correctly to classify as either significant or no insignificant. But the number of pregnancies actually because for the number of pregnancies actually it's not significant. So this one actually it means if we run a model, actually we got those incorrect answer. And for the age, it's about half. So that's why we actually prefer to the result based those patterns. And the future more because some people ask once raised a concern, maybe because the senior person actually there's just very few senior persons. It's true, based on those confident band. Yeah. So then what I did actually, I just simply cut the data just to the age 60. So even with those subset data, and then we feed the data again, and then actually we still observe the similar pattern with at about a 50 with they got the highest risk to got the diabetes. And furthermore, if we just simply calculate the frequency, calculate the signal. So here actually the green dots for the green dots. So if we use the logistic, actually this is the blue line based on, and the red line, I mean our models, then much better to fit the those frequencies. So again, maybe this also support our generalized partial additive model fit data, and got those nonlinear curves are more reasonable. Okay, so then this is still generalized partial linear additive model, but now if we think about it, it's high dimensional, because it lasts more than 20 years talk about variable selection. So here is another real data analysis talk about breast cancer. We are interested in some here we have a 97 lymph node negative breast cancer patient, and for those patients, 46 development distance metastasis within 5 years, but other 51 free for at least 5 years. So in this data analysis, actually it means we only have 97. The sample size is 97. And we are interested in some genes. And of course, originally we have maybe more than 1 million. After we do some pre-screening, so we pick up 200 genes in our data analysis. And for those high dimension, of course, we first faced a challenge. Which one we should put in the linear part, and which one we should put in the non-linear part. And so far, actually, it's another challenging question. So far, no very satisfactory answer. But we just naively classify. First we just do one by one. Means we just run a non-parametric logistic regression for each genes. Use polynomial spline, but of course with a smoothing penalty to panel the second derivative of those non-parametric functions. So based on those classifications strategy, we found 73 genes maybe in a non-parametric part, and the rest 127 genes in parametric part. So for instance, here I show you those 6 genes. Then the second, the 5th, the 6th, those we will classify in the non-linear non-parametric group, and the 1st and the 3rd and the 4th we will be in linear group. Then we do data analysis, use our method. And then simultaneously, we also run a linear logistic regression. So this is the result. Well, actually, we did variable selection. So if we use the logistic regression, we identify 12 linear components or 12 genes. And if we use our generalized partial linear additive model and with adaptive lasso, then we identify 11 linear genes and 4 non-linear genes as significant. And by the way, their character prediction actually pretty close to each other. So for logistic with 81, and for generalized partial additive model with 82. Of course, this just show us both from prediction aspect that seems both similarly. However, because in this study we are more interested which gene important or significant. So we are more care about variable selection, not just for prediction. So here for genes as a illustration. First, look at the lower panel. Of course, the blue lines are based on linear or logistic regression, and the red line based on our generalized partial additive model. So for the lower two genes, no matter we use linear or non-linear, there seems both show us significant, both significant. So that's fine. If we just interested which genes is significant or not, then use the linear or non-linear, it's fine. However, for the up panel, those two genes, if we use logistic model, they show us those two genes actually not significant. But if we use a non-linear, actually they seem significant. Well, of course, from this aspect, the first one looks pretty much like a noise, right? However, for those two genes, we futurely check the region. So for the first genes, we found some medical literature who actually already found that this gene involved in ubiquitin protein some paths. This seems involves several human disease. And for the second gene, this one. We also found those two medical publications. They already identify this gene is a positive regulate of apoptosis. And also this gene maps to chromosome 3p21, and this one actually this region actually highly suspected to some like a human cancer. Both actually long time ago, those two articles already found. Well, of course, this is just some supportive information to feel those two genes may be also related to those breast cancer, and then it is at least it's better than to think they are not important. Just simply kick off. So for those two genes, if we use a logistic model, then we can definitely we cannot detect them. But if we use our general partial linear additive models, they still keep in our group. We may need to do additional experiment to verify that. Okay, so roughly speaking, or briefly, for semi-parametric model, they are somehow enjoy the advantage of parametric model. For instance, for partial linear model, they enjoy a linear model, and also enjoy feasibility. So somehow like data driven, and so they also avoid model misspecification. So they can enjoy some robustness. So this robustness, of course, is not like a robust method, but a robust of the model. So this will be very useful for data exploratory. For instance, if we just got the data and you want to explore some relationship or the couple of variables, then we prefer not to make too strong model assumptions. And of course, we gained something. Of course, then we lost something. For at least the model a little bit more complex. And so this also should be in mind don't try to avoid overfit because sometimes too flexible, that means overfit or over parameterization. And so if we feel we can simplify to the simple model, of course we should choose that simple model then compress the semi-parametric model. And the second one is interpretability. So some maybe not that easy to integrate. So this let me also try to answer Adam's question: how to interpret the y-x for the non-linear. May not directly as a linear model. For instance, for linear model, we can easily interpret the beta. Okay, so beta is just x change one unit and then y change the beta. But for the non-parametric, of course, we can still use the similarity principle. However, it's not that directly like for the linear model. However, if we use the their derivative or something like that, that means we can when x change one unit, then what is the change of y? So similarly for the non-parametric model, we can still interpret it, but not directly as for the linear model. So again, it is usually preferable to rely on a simple and a well understood model for predicting future case than a compressed model, because that is sometimes it's difficult. But however, at the initial stage, make the model a little bit more feasible can make us avoid any seriously business specification assumptions, and can also guide us, help us to reduce or simplify to a simple model for future study. Okay, I think I think that's all of my talk. Thank you.
Thank you, Hua, for a nice talk. We have a few minutes for questions. There is a question in the messaging by Adam Dugan. Could you explain how we should interpret the y-axis in the nonlinear effect plots?
Non-linear. Okay, so if y is a nonlinear, for instance, in traditional logistic regression, we generally know beta is like a log odds ratio, right? So easy to interpret. For the nonlinear, of course, we can say that the distance or the derivative of those nonlinear functions somehow like log odds ratio. But of course, this actually is not a constant like in traditional logistic, because the traditional logistic they're always the same. So, but for the generalized case, that means their log odds actually depend on x. So I'm not sure this address your question.
The answer is yes, that helps by Adam.
Okay, thank you.
Also, you can put questions in the chat, or you can just, Hua, if you maybe switch off, remove the slide,
Yes.
and then we can see the participants, they have questions.
Yes, I can see that. So another one, who can see your message recorded on? Yes, I think Elaine recorded, and it seems publicly acceptable, right?
Yes.
Yeah.
Yes. Yeah.
Any other questions for Hua? You may just ask question verbally, or maybe put in the chat.
Yeah, even later, if you after talk, if you think, okay, I forgot to ask questions, well, you can still email me.
Well, as Hua said, if you have questions, here we go. There is another question by Jennifer Bryant. She's asking, can you put up slide that describes the R package? I did not get chance to write down the name.
Okay, yeah. Well, because actually, it's kind of a shorter talk, but actually it involves several projects and also several data sets. So if you are interested in any specific one, maybe I cannot send you a data, but I can, if you are interested in which one, then I can tell you. And generally, I use the R package, MGCV. Okay, maybe I can type here, chat, MGCV.
Okay.
Yeah, but for others, like because here, we at least 3 projects actually from my 3 articles, and that we developed, variable selection. So some programs may be a little bit sophisticated. And for the first one I mentioned, it's a PLMDE, the package for the first one.
The question by Vered Madar, do you see these GP-LAM models useful in supervised machine learning?
That's a good question. Actually, I'm learning some, machine learning and AI recently. So try to integrate my own research in this, new area. I believe it should be because recently some people already did similar work. They published paper in Annals. Actually, of course, they talk about survival data. I think one of authors is Jenny Wang. So it's highly possible. It's highly possible to extend it or integrate my method to machine learning.
Any other question? You can just ask verbally, not necessarily via chat.
Yeah, feel free either way.
Diana Shimic is asking, what are the pitfalls we have to look out in the using GP-LAM?
Well, so far I didn't find any typical pitfalls. Of course, if you must say, then probably more complicated compared to GRM or something like that.
Okay, I guess these are the questions. If you have more questions, feel free to send to Hua the questions directly. The slides, actually the presentation is recorded. It is going to be posted on our webpage. And I would like to thank Hua Liang for nice presentation, very sort of educative, and thank everybody for attending. So we cannot do applause, but let me do applause for all of
Thank
us.
you so much. Thank you for your time. You know, yeah, hopefully, future somewhere we can see each other and say hello. Yeah, I checked the list. I recognize some of my friends are actually also there, but unfortunately, I cannot individually say thank you. But anyway.
Yes.
Yeah. Okay. So see you somewhere. But at least maybe some future
Yeah.
Aggie reunion in JSN.
Aggie reunion next year.
Yeah. Yeah. Possibly. Yeah.
And I'm inviting everybody to Aggie reunion next year. Whoever attends joint statistical meeting, please join.
Okay. Yeah. Thank you so much, Brian. Thank you, Elaine.